Hi everyone, this is chapter 2 on the chemical level of organization. So as we saw with chapter 1, the first thing you'll see is your learning objectives. So you'll want to take a look at these both before and after you have studied this chapter to make sure you picked up all the information. So why do we need to understand chemistry? You might be asking yourself that right now. You're thinking, this is a biology course. I want to be a nurse, or I want to be a rad tech, or I want to be a PT. All the things that you guys are aspiring to do. Why in the world do I have to have chemistry? Well, understanding the building blocks of the human body helps us to understand how our body functions. Changes at the atomic level significantly affect homeostasis that we talked about in our last chapter, and responsiveness of the neurons and muscles that we'll be talking about in future chapters. Changes in pH cause malfunctioning in proteins and interferes with oxygen transport and hormone functions. And understanding chemistry and biochemistry helps to determine the most effective solution to use to treat dehydration and fluid loss, two very big concerns in healthcare. So we're not going to do anything crazy. We're not going to solve Avogadro's number or balance equations or any of those kinds of things that you might remember from another chemistry course that you had to take. We're going to understand the chemistry that is associated with biology. And so that's a pretty narrow, limited scope. So don't get all panicky here about what we're about to do. This is not nearly as awful as some of you may have experienced in a full-blown chemistry course. So let's start with talking about matter. So matter is anything that occupies space and has mass. I just always say it's stuff. It's everything. Your computer, your shoes, you are all examples of matter. It is composed of elements. An element is a substance that is distinguished from any other matter by the fact that it cannot be created or broken down by ordinary chemical means. By ordinary chemical means. That doesn't include superconducting colliders and all that kind of stuff that they work on in Switzerland and things like that. This is just in ordinary labs. We cannot break this down or we cannot create it. So we have matter. Matter is made of elements. Elements are composed of atoms, and atoms are going to be composed of subatomic particles that we're going to talk about for this course are protons, neutrons, and electrons. There are other subatomic particles like quarks and neutrinos and all that sort of stuff. That is not our concern. Our concern is protons, neutrons, and electrons. So we're going to keep it real basic. What are some of the elements that are found in the human body? There's four elements that form the bulk of the body. That is oxygen, carbon, hydrogen, and nitrogen. Additionally, there are 9 essential elements, and there are 11 important elements, or sometimes referred to as trace elements. So you can see that there's a 24 elements that have impact in human functioning. So just a quick brief view of the periodic table. You do not have to memorize this thing or anything crazy like that. You can always pull a periodic table up on your phone if you needed to. I just wanted you to see that there is this organizational chart and what that chart is all about. So that chart, they have in the very center of it, you see the kind of yellow, light yellow box that they've pulled out, and they've shown you all of the different things that you can read from the periodic table. And so you can find things like the atomic number, which is up in the upper left-hand corner. The atomic number is the number of protons that an atom has. It tells you the name, chlorine, and it gives you its official abbreviation. So the abbreviation is a 1 or 2 word symbol that is internationally recognized. You don't get to make up your own. But there it is for chlorine. And then on the upper right-hand corner in this particular periodic table, it has the mass number. That is the neutron, the weight of the neutrons plus the weight of the protons. All of those are important things to know. And it's all very organized. If we start over on the far left-hand corner of the table itself, up in the upper left-hand corner, we have hydrogen. And you notice up in the corner, hydrogen has a proton number of 1. And if we skirt all the way over to to the other side, you see there is box number 2, that's helium. So it has got a 2 in that upper left-hand corner for its atomic number, and that tells us it has 2 protons. If we go back to the left-hand side, you see we have lithium, beryllium, and then passing over to boron, carbon, nitrogen, oxygen, fluorine, and neon, etc., etc. So you can see how this is very nicely organized for us to look at. So you can see that there's a lot of stuff on here that we never, ever, ever look at in a biology course. It's not our focus. We're just going to be sticking with those very basic elements in the upper 2 or 3 or 4 at the very most rows. So let's talk about atoms for a few minutes. So I mentioned earlier that elements are composed of atoms, and atoms are defined as the smallest quantity of an element that can retain the unique properties of that element. So each of those elements on that chart are different from one another. They're different in their physical properties. They're different in all kinds of things about them, how many protons they have, all that sort of thing, what they look like, what they smell like, if they have a smell, all those kind of things. They're unique from one another in that way. And so each of those elements has its particles that are making it up, and those are the atoms. So if we have an atom of hydrogen, it is what they call a unit of hydrogen. That's the smallest amount of hydrogen that can exist as hydrogen, a single atom. Atoms are referred to, as I mentioned earlier, by 1 or 2 letters: H for hydrogen, for example, O for oxygen, C for carbon. Again, you do not have to memorize these. Some of them you probably already know, like H2O. I think most people know this as the chemical formula for water, and that's 2 hydrogens with 1 oxygen. You can always look that stuff up. So typically it's the first letter of that particular element, although sometimes the letters that you see are in Latin, like sodium is Na for natrium, which is Latin for that, or kalium, K for potassium. All right, so sometimes they've used that. If we get further on down in the chart, if you have to go on and take a chemistry course, the names have other significance that you see. Maybe it's named after the scientist that discovered it, or some part of the world, or something like that. But the ones up there in the very top that we're dealing with are pretty straightforward. Let's look at atomic structure. So atoms are made up of 3 atomic subparticles that I mentioned earlier. There are others. Again, we do not concern ourselves with those. So we're going to talk about protons, which are positively charged. So proton starts with a P, and positively charged starts with a P. So protons are positive. They have a mass of 1 atomic unit, 1 atomic mass unit, or 1 AMU, if we were to assign it a weight, if you will. Neutrons are neutral. They have no charge. So neutron starts with an N and no starts with an N. So neutrons have a neutral charge. They also have a mass. Now, they don't have a charge, but they do have a mass that is equivalent of a proton of 1 AMU. And then we have electrons. Electrons don't have a fancy little mnemonic. Electrons start with an E and negative starts with an N, and I don't know how to make that make sense to you, but that's just the way it is. These are so tiny, 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 they virtually have no weight. They're 1/2000th of an AMU. So we say, just for the sake of argument, that they have no mass. So taking a look on the right-hand side, you see we're looking at helium, and helium has an atomic number of 2. And so there would be 2 protons in that nuclear area, and then we would have 2 electrons. Because when we talk about an atom, if we know the number of protons, because we can look at our periodic table, we automatically know the number of electrons. Right? So if we know we have 2 protons, if we're talking about an atom, because an atom is a neutrally charged particle, it does not have a charge, if we have 2 positives in the nucleus, then we must have 2 electrons out in what they call the orbitals, or the area outside of the nucleus. All right? So atoms of different elements are going to contain different numbers of subatomic particles. That should make sense to you after looking at the periodic table, right? Hydrogen has 1, helium has 2, all right? Lithium has 3. The number of protons determines the element. That's how that's organized. That whole chart is organized by the number of protons. The electrons are found in the energy levels that are called the electron shells that are surrounding the nuclear area. The electron shells have different numbers of electrons, and the number of electrons that we're going to see is going to be equal to the number of protons. So we use this statement when we talk about an atom where we say P equals E. Protons equal electrons. So again, you already know the number of protons if you can look at a periodic table. Because if you can see a periodic table and you see that atomic number is the number of protons. So you know that information, and then you can surmise from that that if it has an atom, meaning it's neutrally charged, that if it has 4 protons, then it must have 4 electrons. If it has 10 protons, then it must have 10 electrons. Atomic charge. Again, an atom is considered neutral. When we say the word atom, we are making the assumption it is neutral, since the number of protons always equals the number of electrons. P equals E. Protons and electrons, again, are located in the center of the area, the nuclear area, sometimes called the nucleus, which is kind of confusing because in the next chapter, we're going to be talking about the nucleus of the cell, and the nucleus of a eukaryotic cell is clearly defined, and it is compartmentalized with its own specialized membrane around it. Well, an atom doesn't have that. It's just an area where we find the neutrons and the protons clustered. So I just don't want you to be confused about that. It's a nuclear area, the center of the atom. Again, the electrons are found orbiting in the around that proton-neutron mass that's in the middle. So we look at this 2 ways. If we're going to draw it out, you see the top schematic there where you actually have the drawing. In a lot of books, what you'll see is the nucleus with the protons and the neutrons in the center there, and then you'll just see this blue haze around it, indicating this is where the electrons are found, because the electrons are always in motion. That first picture is very static, as if we took a photograph. The second one is more like a video, because electrons are always moving around, so it would be more of a big blur, is where we would find those electrons, not some static position like we see in the top picture. All right, let's talk a little bit about the arrangement of those electrons in the orbitals around the nucleus. So atoms can have up to 7 electron shells. So that's a really big atom. We're only going to study the first 3 in this particular course. So let's talk about where those electrons could be found. If we could just take a snapshot of an atom, where would we expect to find the electrons? So each shell can hold a limited number of electrons. That's called the octet rule or the rule of eights. The first shell can hold up to 2. The second and third shell can each hold 8. The electrons are going to fill the lower shell before moving to the higher one. So it's not like going to the grocery store where you just find any parking spot you can find. This is a very orderly sequence. The first 2 electrons are going to go in the first shell. The next 8 are going to go in the second shell. And the next 8 are going to go into the third shell. So let's take a look at the drawings over on the right-hand side. Remember always that protons equal electrons. So our first atom is hydrogen. Hydrogen has 1 proton, so it has 1 electron, and we would expect to find it in that first shell. And then helium has 2, as we've seen before. It has 2 electrons. We would expect to find those in the first shell. And then we'll just quickly look at the example of carbon. Carbon has 6 protons, therefore it has 6 electrons. We find 2 in the first shell and 4 in the second. The outermost shell, whatever it is, even if it's just that very first one, that outermost shell that it has is called the valence. And that is important because that's where all of the activity for bonding that we're going to talk about in a few minutes is going to happen. Some atoms are most stable when they have 8 or 2, if it's just the first shell, electrons in their outermost shell. I always say it like this. Atoms want to be happy. They want their outermost shell to be full. And so they're going to beg, borrow, and steal to get that outermost shell full. All right. All of our chemical reactions that we're going to be talking about occur between electrons in the valence shell of neighboring atoms. So when we're going to be talking about how we're going to fill up these shells and we're going to borrow and we're going to accept and we're going to donate and all that stuff that we talk about with bonding, how is that going to happen? It's all happening in that outermost shell. All right. So if we take the case of hydrogen, hydrogen only has 1 shell because it only has 1 proton and it has 1 electron. That outermost shell where that electron is, that is its valence. If we look at sodium, sodium has 2 shells. Its valence is that outermost shell. All right. The thing to remember, though, is if we change the number of electrons by making the atom happy to get a full outer shell, then we're going to change the charge on that atom. And that's a really important idea because remember, P equals E when we're talking about an atom. But if we're trying to fill that outermost shell, and to fill that outermost shell, we have to gain some electrons, we are now changing the electrical charge on that atom. It's no longer an atom. It's going to become what's called an ion because it has the same number of protons. It always has the same number of protons, but now P does not equal E anymore. Most of the atoms do not have 8 electrons in their valence, therefore they engage in reactions with neighboring atoms to either gain, lose, or share electrons to fill their valence shell. The elements in the last row of the periodic tables, if you go back to the very last row that we talked about, those when we draw what's called the electron configuration, in other words, if I said, hey, tell me where the electrons would be, and you knew what the proton number was, so you could make the little quick drawing there, and you could put 2 in the first shell and 8 in the second shell and 8 in the third shell, and you could figure out where those electrons were at any given moment. The elements in the very last column that start with hydrogen, those elements right there, if we draw them, their outermost shell would already be full. And so they don't engage in chemical reactions because they're already happy. They don't need to gain electrons or lose electrons or share electrons or anything like that. They're already happy. So we refer to that very last row on the periodic table as the noble gases, and they are considered inert. In other words, they don't react. But that's not the case for everybody else. So let's talk about the 3 big I words, in chemistry: ion, isotope, and isomer. An ion is an atom that has a different number of electrons than protons. So ions are all about the electrons. And so that we just looked at. So if we're trying to fill that outermost shell and we gain electrons or we lose electrons, we no longer can be called an atom because P does not equal E, right? And so when P doesn't equal E, then we have an ion. And there's 2 ways to be an ion. A cation is an atom that has lost 1 or more electrons and now has a positive charge. So you're thinking to yourself, wait a second here. Got to remember that electrons have a negative charge. So if we lose them, then we have more protons than we do electrons, and protons have a positive charge. All right, P does no longer equals E, and we have more protons than we do electrons, so we have a cation. And some people say to remember the word cation is positive because the T kind of looks like a plus sign. So if that helps you, I hope that helps you. An anion is an atom that has gained 1 or more electrons and therefore now has an overall negative charge. So again, you're saying to yourself, wait a second, we're gaining something and it's negative. Yes, because electrons have a negative charge. P does not equal E. Now we have more electrons, which are negative, than we do positives, which are protons, which are positive. And so our overall charge is going to be negative. And so an anion is an atom that has gained electrons and is now got a negative charge. And I don't have a fancy way to remember that. Just remember cation, and anion has to be the other way. Isotopes, the next I word. So ions was all about changes in the number of electrons. Isotopes are an atom with a different number of neutrons. Remember neutrons? Neutrons have no charge, but they had the same mass as a proton. So that doesn't change the charge on the atom, but it does change the mass because neutrons have a mass of 1 AMU. So isotopes are about different numbers of neutrons. So an isotope of an atom is going to degrade and give off radiation as they attempt to become more stable. And in doing so, we are able to pick this up on radiation with imaging equipment, which is what RadTech is all about, right? So isotopes are about different numbers of neutrons. And so an atom can have a whole bunch of different numbers of neutrons. So you can have different atoms within an element that have different numbers of neutrons. Hydrogen is an example of that. Hydrogen can have 1 it always has one electron because it's hydrogen. It has one atom, one proton, but it can have one neutron, it can have two neutrons, or it can have three neutrons. And so if we keep adding the number of neutrons, it's going to weigh more. It's going to have more mass. And so hydrogen 1, hydrogen 2, and hydrogen 3 are different from one another. And then finally, we're going to talk about isomers. Isomers are a molecule, so this is not a single atom, but a molecule, which is atoms that have bonded together, that has the same chemical formula as another atom, another molecule, but they're arranged differently. So I always say, I want you to think about it like this. Let's pretend we're building a house. And just for simplicity, let's say we're building a 3-bedroom, 2-bath house with a kitchen and a dining room and a living room, right? And it's 1,500 square feet. There's a lot of ways we could arrange that, isn't it? If we did our floor plan, we could make a lot of different arrangements to get a 3-bedroom, 2-bath home, right? We could do a split master. You could do the master, all the bedrooms together. You could put the master on the bottom floor and the other two on the upper floor. There's a lot of ways we could arrange that, but it's still a 3-bedroom, 2-bath, 1,500 square foot home. That's how isomers are. We have a molecule that has a specific formula, but there's a lot of ways we can arrange the atoms that are making that up. And so the classic example for this is the different sugars of glucose and fructose. So glucose has a molecular formula of C6H12O6, meaning there are 6 carbons, 12 hydrogens, and 6 oxygens. But there's a lot of ways you can arrange that. All right. They all have the carbon backbone. You can see the picture of that. But where those hydrogens and oxygens are arranged and all that sort of stuff, they can be slightly different from each other. So you can have glucose and you can have fructose. And glucose and fructose both have the same molecular formula. You can see that underneath of the word for glucose and fructose. But they have different arrangements when you look at the blue box. Okay? And so that's what an isomer is. It's just a different arrangement of that molecule. Sometimes isomers can be detrimental, and that's why it's important to understand them, especially in pharmaceutical drugs. So there is a lot of information out there about a drug called thalidomide. Thalidomide. So thalidomide was released in the late 50s, early 60s, and what they didn't know was that there was an isomer of it that that would behave very badly in the human body. So it was released as an anti-nausea drug for pregnant women because women often undergo really bad nausea in that first trimester. And so thalidomide was given to those women. And unfortunately, there was an isomer, a different arrangement of that molecular formula that could have teratogenic effects on unborn babies. In other words, it could cause birth defects. And if the mom happened to take that medication when the limbs were budding for the arms and the legs in early pregnancy, um, it could stop that process. And so thalidomide babies were born mostly in England. There were a few in the United States, but mostly in England. And those babies didn't have arms or legs, or they had partial arms and legs. And so obviously there was something wrong with the drug and they took it off the market and they studied it and found out what was going on. It was an isomer. It's called a diasteric isomer that has really bad side effects that it can cause. They use thalidomide now, again, for other reasons, but you have to 100% guarantee that your patient is not pregnant or will become pregnant while they're on that. They use it for HIV patients. It has some promises in a lot of areas, but it does have some really bad isomers that can cause issues. So those are our 3 I words. I want you to make sure you have those down. Ions are all about the difference in the number of electrons. Isotopes are all about differences in the number of neutrons. And isomers are all about differences in the arrangement of a molecule. So make sure you've got those down because those words will come up intermittently throughout our lectures and throughout your career. Let's talk about compounds and molecules. So a bond is a weak or strong electrical attraction between electrons of neighboring atoms. It's not an actual physical structure. We draw it like it is, but it's not. It's just an electrical attraction. It's like two magnets. So we see two magnets. If you've ever played with magnets before, you know that they kind of try to pull towards each other on the negative and the positive end, try to pull towards each other. There's not an actual physical bond between them. It's just an attraction. And that's what a bond is. When we have two identical atoms that form a bond, they form a molecule. So if we've got two hydrogens or two oxygens or two carbons, then we call that a molecular oxygen or a molecular hydrogen. And the formula for that would be the capital letter, the symbol, and then a subscript 2 next to it. All right, that would tell us that we have two of the same atom. If the atoms that form the bond are different, they form a compound. And we just looked at one, C6H12O6, which is a molecular formula again for glucose. And that is a compound because the atoms are not the same. We have 6 of some of them and 12 of the hydrogens, but the overall molecule put together is not identical. Because of the octet rule, atoms arrange in chemical reactions to either gain, lose, or share electrons, and to have those 8 electrons in their valence shell. There's 3 types of chemical bonds that are going to be discussed in this course. Again, there are other kinds, but that is left for courses that we don't have to take. Right, so we're going to look at ionic bonds, covalent bonds, and hydrogen bonds. All right, let's talk about ionic bonds first. When atoms lose or gain electrons, they become ions. You guys already know that. If in the ions, the number of protons and the electrons is not equal because P does not equal E anymore, atoms are going to lose or gain electrons to have 8 electrons in their valence shell. And as you remember, if the atom loses an electron, it becomes a cation. Cations are positively charged ions. And the atom gains an electron, it becomes an anion. Anions are negatively charged ions. So let's see how this works with sodium chloride. This is the classic example. This is how we form table salt. So sodium is an atom that has 11 protons. So let's figure out where its electrons are. It has 2 in the first ring. It has 8 in the second ring, and it has 1 in the outermost ring. 2 plus 8 plus 1 is 11. If we had 11 protons, we know we have 11 electrons. All right. Chloride, let's take a look at it for a second. Chloride has an atomic number of 17. It has 2 in the first shell, 8 in the second, and 7 in that outermost shell. So would it be easier for sodium to find 7 other electrons for that outermost shell, or just give up the one that it has? It'd be easier to give up the one it has, right? And when it does that, it's going to lose that electron and it's going to become a cation. It's now going to have a positive charge because it's going to have 11 protons, but it's only going to have 10 electrons. So it's got more protons than electrons. So it's going to have an overall positive charge. Chlorine, it either has to get rid of those 7 in the outermost ring or just take on one more. And so it's going to take on one more. And in doing so, it's going to become an anion. It's going to have 17 protons, but 18 electrons. Okay. And so it is going to have an overall negative charge. Sodium has an overall positive charge. And now they're attracted to each other and they're going to form ordinary table salt. So that opposite charges of the two are going to cause an attraction between the two atoms, and that is what we call the ionic bond. So here is a picture of what it looks like. So it's interesting when we look at this because sodium, if we look at pure sodium, is a silver metal. If we look at pure chlorine, it is a green poisonous gas. But the two of them together make ordinary table salt. So the formation of most of our salts are the result of ionic bonding. Salts form crystals when they dry, and salts can easily disassociate or break apart in water. When we put salt into water, it breaks apart and the ions are released. And now the solution that we've made by separating the sodium and the chloride from each other because they're anions has a weak electrical charge. The sodium and chloride, once dissociated, remain ions. They don't go back together. So that's ionic bonding. Now let's talk about covalent bonding. So let's start with talking about what covalent means. So co means to share. Valent is referring to that valence shell, the outermost ring that we were talking about earlier when we draw the electron configuration. So covalent bonds are not going to give up their electrons, or they're not going to accept electrons. Covalent bonds are going to be formed when we decide to share electrons. Okay, so we're not accepting or donating, we're sharing. And we can share either equally or unequally. So there's two different types of covalent bonds that we'll talk about here. Non-polar covalent bonds mean that we are sharing the electrons equally, and polar covalent bonds mean that we are not sharing the electrons equally. Single, double, and triple covalent bonds, this is the sharing of two electrons in a single bond. So if we are sharing two electrons between two atoms, we have a single bond. An example of this is a hydrogen molecule. Remember, hydrogen only has one electron in its outermost shell, and it wants to, and the other electron, the other hydrogen has one in its outermost shell, and it wants to. So to compromise, they're going to share that. Sharing four electrons is what we call a double bond. So we do molecular oxygen or carbon dioxide is another example of that. And sharing six electrons produces a triple bond. A nitrogen molecule is one that does this. Triple bonds are extremely explosive. So you won't find any of these in the human body. Triple bonds are what make TNT or dynamite. So let's talk about the difference between polar and non-polar bonds. So a non-polar covalent bond, the electrons are going to spend equal time with each atom and the electrons are shared equally. Why is that? Because when we look at the number of protons in the two atoms, because they're the same, they have the same pull on the electron. So let's have one hydrogen on one side and another hydrogen on the other side. So we're going to be sharing the electrons between the two of them. Both hydrogens have one proton, which is a positive charge, and they're both pulling equally on that little negative electron. So they end up sharing it equally. So we end up with a neutral nonpolar compound, like carbon dioxide is another example of that. In polar covalent bonds, the electrons are going to spend more time with the larger atom. The electrons are going to be shared unequally. That larger atom is going to have more protons, therefore more positive pull on those little electrons. This produces electrically unequal molecules. One has a positive end and one has a negative end because of the unequal sharing. So water is our classic example of a polar molecule. Oxygen has way more protons than poor little hydrogen. So it pulls those shared electrons from the two hydrogen atoms. So water is two hydrogens in a polar covalent bond with one oxygen. So when that happens, because the electrons spend more of their time with the oxygen, we end up with a slight or partial negative charge on the oxygen end of the molecule, and that's represented with that squiggly line S and the negative behind it. And the hydrogen end has a slightly positive end because it never gets to have the electron. So it's been stripped of its electrons. It's basically just a proton by itself there. And it has a squiggly line with a little plus sign. And so they're showing you that in the picture, how the electrons are going to spend more time with the larger molecule or larger atom. So that leads us to our third type of bonding, and is called hydrogen bonding. So hydrogen bonding is going to happen when we have polar covalent molecules that have that slight negative charge on one end and slight positive on the other. When the slight negative of one polar covalent molecule is attracted to the slight positive end of another polar covalent molecule, we have what's called a hydrogen bond. So when we were talking about ionic and covalent, those are how we actually make a molecule. Now, how are these molecules attracted to each other? if we have a polar covalent situation, we form hydrogen bonds, which is more of a weak attraction rather than a bond like we've been talking about. All right, and so that's what we're seeing here in this particular picture. We've got water molecules, and remember the hydrogen end of a water molecule has a positive charge because it's lost its electrons to the big old oxygen. And the oxygen end has a slight negative charge because it's getting to use electrons all the time. So the electrons with their negative charge are on that end. So the positive end of one water molecule is attracted to the negative end of another water molecule. And in that process, we form a hydrogen bond. So hydrogen bonds are always represented with a dashed line. So we see these sticks, these straight lines for covalent and ionic bonds, but we see a dashed line that represents a hydrogen bond. And so we see that this is the hydrogen bonds that are formed between water molecules. Hydrogen bonds give water a lot of really unique properties. One of the properties that it gives them is its ability to flow. So when you open your faucet, turn your faucet on, water molecules do not come out as individual beads, right? They come out as one cohesive unit. And that's because of this hydrogen bonding. These bonds, these hydrogen bonds that are formed, this temporary attraction, it's instantaneous. They form and they break and they form and they break and they form and they break. And because of that, it gives water the ability to flow. So there's a lot of interesting other things like surface tension, those kinds of things that are the result of hydrogen bonding. So hydrogen bonding is really important idea to understand about how molecular formulas or molecular compounds are put together. Switching gears for a few minutes, let's talk about chemical reactions. So a chemical reaction is the result of a chemical bond formation, rearrangement, or breakage. So what's the big deal about bonds? Well, here's the big deal. Energy is formed in bonds. When we put bonds together, we put molecules together or atoms together to make molecules, we make a bond and we store energy in that bond. When we break that molecule apart, we break those bonds, we liberate energy. And that's a really super important idea, especially when we start talking about ATP at the end of the chapter. All right, so that's what a chemical reaction is. It's a formation of a bond, a breaking of a bond, a rearranging of the bond. So we have a chemical equation that we use to write these in symbolic forms. So if you look at the bottom of the page, we have 2A plus B. It means we have two atoms of A and one atom of B. And when we bond them together, they form A2B. All right. And so the reactants are the substances that are going to enter into the reaction, typically on the left-hand side of the equation, and the product is what we make from that. The numbers in front tell you how many we have that are unbonded. So 2A tells us that we have two of atom A. And then if we have a subscript number behind it, that indicates that they're already bonded. All right, there's three main types of chemical reactions that we're going to talk about. Synthesis means to build. So the chemical reaction results in the bonding components that were formerly separated. We're going to put things together and we end up with a larger molecule, and we refer to this as anabolic. We are building. So we use a synthesis reaction to build things. So A plus B is going to lead to AB. All right, and so we give you the example of amino acids that are bonded together to form a protein. Decomposition is just the opposite of that. This is a chemical reaction that's going to break down or decompose something that's larger into smaller pieces. This is going to break the large molecule into smaller ones, and that is referred to as being catabolic. So we started with AB and we ended up with A plus B. So we made proteins a few minutes ago by putting amino acids together, bonding them together. Now we can break those amino acids, those proteins apart into the individual amino acids. And then we can have exchange reactions. This is when we have both synthesis and decomposition occurring. I call it the big square dance of life because we end up with bonds being broken between two compounds and then reformed between two different compounds. So everybody switches partners here. All right. And that's what they're showing you. AB plus C leads to AC plus B, and we could have AB plus CD, and we could break the bond between A and B and the bond between C and D, and then repair those A and D and C and B. All right, so that's what an exchange reaction is. In theory, all of these chemical reactions we're talking about are reversible, and in the lab they absolutely are. So if we're sitting in the lab with a bunch of test tubes, we can make those molecules or those compounds join together and break them apart, and join together and break apart over and over and over again, right? And we see that the A plus B leads to the arrows are the same length, right? Leads to AB, and that AB leads to A plus B. In living systems, though, that doesn't happen. Theoretically, it could, but the whole point of putting molecules together or breaking molecules apart in living systems is to use the products. And so the products get consumed and they never engage reversibility. So they could happen if we had if we didn't need them, and sometimes that is the case. If we don't need them, we rebuild them. But for the most part, we don't see that in living systems, unlike what we see in our labs. Okay, how quickly do our chemical reactions happen? What is the rate? Depends on a lot of things, including the property of the reactants. So if the reactants have more surface area, they are able to readily interact easier with one another. Temperature, when we increase the temperature, the more likely they are to react to a limit in living systems. In labs, we don't have those limits, but in living systems we do, because there is a biological limit on the temperature of a living thing. Concentration and pressure. Chemists can speed up chemical reactions by increasing the concentration of particles. That should make sense to you. If we have more of them in the same space, then we have a more likelihood that they're going to combine with each other, right? So we can also do this by increasing or decreasing the volume, which would increase the pressure, right? So when we think about pressure and volume relationships, let's take this example right here. Let's say I clear all of the furniture out of the room that you're in, and there's a whole bunch of people in that room, right? And we put blindfolds on everybody, and everybody gets to walk around. And so pretty soon you'll start bumping into each other and the walls because you can't see each other, right? And that's exactly what happens with a chemical reaction. The molecule, the atoms bump into each other and they have a chemical reaction when that happens, right? Well, let's just say and there's a certain amount of pressure that's created by all this interaction between you bumping into each other. Let's take that room and remove half of the size of that room. Let's shrink the room down by half, but keep the same number of people in there, all blindfolded still. Now you're going to start running into each other in the walls a whole lot more, aren't you? And because you've decreased the volume, you've increased the pressure in the room because there's more collisions happening. And you've also increased the likelihood that you'll have those collisions. And that's what they're talking about with concentration and pressure. Particle size, smaller particles usually are faster. It's just all there is to it. If we look at cars out on the highway, little cars are a lot faster than big cars. Enzymes and other catalysts. A catalyst is a substance that increases the rate of a chemical reaction without becoming part of that reaction. When we do that in a biological system, we call that catalyst an enzyme, right? So a biological catalyst is an enzyme, and we're going to talk about those some more. The catalyst remains unchanged. Typically, enzymes are made of protein. So now we can switch away from that fun inorganic chemistry and move to biochemistry. Biochemistry. So biochemistry is the science that studies chemical composition and reactions within living biological systems. So if you've had to take chemistry in college, you take inorganic chemistry or general chemistry the first time, and then you have to take organic chemistry, which is a beast all unto itself, the second time. And then the third chemistry you take is biochemistry. And then there's more chemistries you take after that that are really hideous. All right, depending on the composition, chemicals can be organic or inorganic. Inorganic compounds is a substance that does not contain both carbon and hydrogen. Water and salt and many acids and bases are considered inorganic. Organic compounds are substances that contain both carbon and hydrogen. So our carbohydrates, fats, proteins, and nucleic acids are examples of organic compounds. We'll start this conversation with talking about water. So 70% approximately of the human body is made of water. This water is contained both within your actual cell itself and between the cells that make up all the tissues and the organs. Water is indispensable for living things. So that includes water being used as a heat sink, water as a component of liquid mixtures, water as a lubricant and cushion, and the role of water in chemical reactions. So we have to have water. I think the old saying is 3 weeks without food, 3 days without water, 3 minutes without oxygen, something like that. So water is critical for living things. So water is a heat sink. A heat sink is any substance or object that can absorb and dissipate heat, but doesn't experience a corresponding increase, or at least any kind of significant corresponding increase in temperature. In the body, the amount of water that we have, because of all of the heat that we generate from chemical reactions, that water is able to absorb all of that heat from muscle contraction and all that sort of stuff that happens without increasing your body temperature significantly. All right, so that's what a water sink is. So water is absorbing all of the heat in our bodies, and then letting that heat off very slowly so that it doesn't damage living tissue. Water as a component of a liquid mixture. So a mixture is a combination of two or more substances, each of which maintains its own chemical identity. Examples of this include oil and water. When we put oil and water together, they don't chemically bond together. They just are a mixture, right? There are three types of liquid mixtures that we're going to talk about here, all of which contain water as their key component. They include solutions, colloids, and suspensions. So a solution consists of two parts, the solvent and the solute. The solute is being dissolved by the solvent. So I want you to think about Kool-Aid for just a minute. When you make Kool-Aid, you have water and you have the little Kool-Aid package. Let's just assume for a second that it has the sugar already in it, right? What's being dissolved is the Kool-Aid package. That's the solute. And what's doing this dissolving is the solvent. So solutions are homogeneous. The solute molecules are distributed evenly throughout the solution when that solution is made. So when you make a solution of Kool-Aid, everything is homogeneous in there. Solutions do not precipitate, meaning they settle out over time. So if you leave that pitcher of Kool-Aid sitting in your refrigerator for a week or a day or however long, it doesn't separate out. It stays a mixture, all nice and mixed up. And then water is considered to be the universal solvent because it's used in so many solutions. So they give you some other examples at the bottom that are a little bit more medically related, like sugar and water and salt and water and blood sugar, not just your standard Kool-Aid mixture, but everybody understands Kool-Aid. Water molecules are polar. They have regions of positive and negative electrical charge. We've seen that already. Water readily dissolves ionic compounds and polar covalent compounds. Polar molecules are hydrophilic, meaning that they love water. Hydro means water, philic means loving. So polar molecules are water loving and they can dissolve easily in water. Those non-polar molecules, the ones that are sharing things equally, they're hydrophobic. They are water fearing and they cannot dissolve in water. We can express concentrations when we talk about solutions in three different ways. We can talk about the percentage. The percentage is the number of solute particles in 100 parts of solution. So for example, if we buy 2% milk, that means 2 parts of fat to 98% parts of milk or water. So 2% and 2 and 98 equal 100%. Milligrams per deciliter, that's abbreviated mg/dl. A deciliter is equal to 1/110th of a liter. So our normal fasting blood sugar numbers are expressed between 70 and 99 milliliters of deciliter per deciliter, meaning that we have that's how much sugar we have dissolved per deciliter of blood. And then finally, molarity, the capital M, which is moles of molecules per liter. So these are all way beyond having to calculate in the scope of this course. So don't worry too much about it. Just know that there's lots of different ways, and you're going to see those. Sometimes you'll see percentages on lab reports, and sometimes you'll see things like milliliters per deciliter, and sometimes like on an IV solution bag, you'll see 1 molar solution. Right? It's just how we're expressing the concentration in a solution. Moving along to colloids. A colloid is like a heavy solution. It's like a gel. It's thicker. The solute particles consist of tiny clumps of molecules large enough to make the liquid mixture opaque, so it's not transparent. Colloids do not settle out or take long, or they take a really long time to settle out if you let them sit there. Some examples of colloids include things like milk. Now, milk will eventually separate out, right? Mayonnaise, it would take a really, really long time for that to happen. And whipped cream. So if you've ever made whipped cream from scratch, from heavy cream, if you let it sit for too long, it separates itself out. But for the duration of while it's on your pumpkin pie, it's perfectly fine. And then there are suspensions. This is a liquid mixture in which a heavier substance is suspended temporarily in the liquid, but over time it's going to settle out. So you see this with salad dressing is a perfect example. If you buy a bottle of an oil-based salad dressing like Italian salad dressing, and you leave it sitting in the refrigerator, you notice it settles out, and then you have to shake it back up. That's the idea of what a suspension is. Water and sand will do this. So if you go to the beach and you mix up water and sand, in the beginning it looks like this kind of sandy looking water, but if you just let it sit there for a few minutes, the sand eventually settles out of that. Blood will do that too. So blood is considered a suspension. Then water as a lubricant and as a cushion. So as a lubricant, water is the major component of a lot of the body's lubricating fluids. Water, for example, in the synovial fluids that are in your joints, lubricates the action of that body joint. Cushioning, water also protects the cells and organs from physical trauma. Your brain is floating in its own solution, cerebrospinal fluid up there that's almost all water, and that helps to protect the tissues of the eye and of the brain itself. The baby is floating around in the amniotic fluid, and that fluid is allowing that baby to avoid any injury as it moves around, it floats around inside of mom's uterus. And let's look at water and chemical reactions. So there's two types of chemical reactions that involve the creation or the consumption of water. So we have dehydration synthesis and hydrolysis. So these reactions are reversible and they play an important role in the chemistry of organic compounds, how we make carbohydrates and proteins and all that sort of stuff. So let's talk about dehydration synthesis. The name, let's look at the name first. Dehydration means to take water out. Synthesis means to build. So literally, we are taking a water molecule out as we build a molecule. All right, and that's exactly what you see happening here. We have our monomer number 1, which is our first building block, and our monomer number 2. We want to put those together in a bond, a covalent bond, and when we do that, we remove a water molecule, and then we have our molecule that's been formed. So dehydration synthesis, a water molecule is removed in the process of making the bond. Hydrolysis, let's look at that term. Hydro means water, lysis means to break apart. And so in this case, when we are breaking apart a bond, we put a water in to do that. All right, so hydrolysis involves putting a water molecule into the system to break a bond. I talked about salts briefly. These are formed from ionic bonds. Salts are going to disassociate or break apart readily and completely in water. The positive and negative region of the water molecule, which is the hydrogen and oxygen ends of that respectively, attract the negative chloride and positive sodium ions and pull them apart from each other. So that is how that happens. The ions that are produced when we break a salt apart are electrolytes. They are capable of conducting an electrical current in solution. The function of ions in transmitting is transmitting nerve impulses and promoting or prompting muscle contraction is critical. So we're going to learn about that later in the semester. So ions are all about your ionic balances being out of out of whack because of dehydration. Those kinds of things are important ideas that you deal with every day in medicine. So ions are extremely important in homeostasis. That moves us to acids and bases. So acids and bases, like salts, are able to dissociate in water and become electrolytes. Acids and bases are going to change the properties of the solution that they have broken apart in, and we can measure that. So we dissolve acids and bases into water, and they at least partially dissociate, sometimes fully dissociate. And when they do that, it changes one of the important properties of that water or of that solution. So an acid is a substance that's going to release hydrogen ions in solution. Hydrogen ions are nothing more than protons. They have no electrons, and in solution, hydrogen ions are going to likely participate in chemical reactions. Some examples of acids are hydrochloric acid, which is considered to be the strongest acid, and carbonic acid, which is considered to be a weak acid. Both are important in the human body. So when we use the term strong and weak, that does not mean its ability to do a lot of damage to the body. What it means is how much of the hydrogen chloride or how much of the carbonic acid actually breaks apart in water. If it completely breaks apart, if all of the bonds are broken, then it's considered a strong acid. If only a few of the bonds are broken, then it's considered a weak acid. So that's the difference between those two. They both can do a lot of damage, but it's just how easily do they disassociate. So that's what strong and weak is referring to in this. So when we put hydrochloric acid in water, it completely disassociates into hydrogen protons and chloride ions. And those hydrogens are what we're measuring in something called pH. A base is a substance that can accept hydrogen ion in solution. Basic substances combine with the hydrogen that's present to form a water molecule, thereby removing the hydrogen ion and reducing the solution's acidity. In many cases, when a base dissolves in a water, it releases hydroxyl. So an example is sodium hydroxide. When it is broken apart, it produces sodium and hydroxyl. Some important bases include bicarbonate acid or bicarbonate ion and ammonia. So why is that important? Because we are measuring something called pH. So pH is your acid-base concentration. You see the little scale over on the right-hand side. It is measuring the negative logarithm of the hydrogen ion concentration. I do not expect you to remember that. What I do want you to know is that it measures the concentration of hydrogen ions. So we're not measuring anything besides the number of the concentration of the hydrogen ions. So the scale goes from 0 to 14 with 7 as our neutral point. Anything from 7 going towards 0 is considered an acid, and it's red on our scale. All right, so 0 to 6.99 is considered an acid, 7 is neutral, and 7.01 going to 14 is considered to be a base. All right, why is this important? Because every whole number we change represents a 10-fold increase or decrease in the acidity or alkalinity of a solution. So pH is a really big deal. So let's just say, for example, that we have a solution that has a pH of 6. If we compare that as compared to how acidic it is to a solution with a pH of 5, 6 to 5 is one number change, but it's 10 times more acidic. So something with a pH of 5 is 10 times more acidic than something with a pH of 6. And it goes the other way as well. If we go from 9 to 10, something with a pH of 9 is more acidic than something, 10 times more acidic than something with a pH of 10. Remember, we're only measuring the acidity. All right. So you can imagine if we're looking at comparing something with a pH of 6 to something with a pH of 4, it's not 2 times more acidic. It's 100 times more acidic to be a pH of 4 because we have to multiply 10 times 10. So it was 10 times more acidic to go from 6 to 5, and another 10 times more acidic to go from 5 to 4. So something with a pH of 4 compared to something with a pH of 6 is 100 times more acidic. And that's a big deal. And so one of the homeostatic mechanisms that we have to maintain all the time is our pH. The pH of blood is right around 7.4. We want to keep it right around 7.4. If it goes too low, we have a condition called acidosis, and that is a really serious condition. It can actually kill your patient. If we go too high, we have become alkalotic, and that can be an issue as well. That's less of a problem because it doesn't happen nearly as often as being acidic does. So all of the chemical reactions that are happening in your body are releasing hydrogen ions, and those hydrogen ions are driving the pH of your blood down. Your blood has a built-in buffering system that I'm going to talk about to keep that from happening. So acids and bases easily react with one another, and when they do so, they produce salt and water. If we have a strong acid and a strong base, they neutralize each other and create a pH of 7. So remember what I said, strong just means how much um, of the compound breaks apart in water, and so it means all of it does when it's strong. Which leads us to buffers that I just referred to a few minutes ago. A buffer is a solution of a weak acid and its conjugate base. Buffers help to protect and prevent large changes in pH. So they can donate hydrogen ions in solution to prevent an increase in the pH, and they can also take up hydrogen ions that aren't bound in solution to prevent a pH change. So they basically are buffering. All right. In the human body, you have the carbonic acid bicarbonate system. That is the most important buffering system of the blood. We'll be talking about this in the second semester of this course, that allow the pH of the blood to remain constant at all times. And we want that. We don't want fluctuations in our blood pH. Moving along to organic compounds. So organic molecules contain carbon and hydrogen. The major ones we're going to talk about here are carbohydrate, lipids, proteins, and nucleic acids. So the word carbohydrate comes from the components that make it up. So carbon, hydrogen, and oxygen. So carb for carbohydrate, for carbon, O for oxygen, and high for hydrogen. So carbohydrate is a combination of carbon, hydrogen, and oxygen. And most of the time we have a 2-to-1 relationship. It's actually what's called a 1-to-1 relationship. For every 1 carbon, we have 2 hydrogens and 1 oxygen. 1-to-1. All right, or 2-to-1 if you want to look at just the things um, that you have 2 of, which is your hydrogens, and 1 carbon and 1 oxygen. The major function of your carbohydrates is to provide energy. We all know that, right? When you are really low on energy, if you have some carbohydrate, then it gives you a quick boost of energy. There's 3 classes that we look at. Monosaccharides, which is a single sugar. The parts that make up any of our organic molecules are called monomers. And so the smallest unit of a carbohydrate is a monomer. I always think about it like Lego. So you have an individual Lego that's a monomer, and we put those together and we make our carbohydrates. So one monomer is a monosaccharide. A disaccharide is 2 Legos put together. A polysaccharide is a whole bunch of Legos put together. The polymers are made up of monomers, of monosaccharides, like I just said, and they're all formed through dehydration synthesis, and they're broken apart through hydrolysis. So looking at this a little bit closer on a monosaccharide, it is the monomer of a carbohydrate and is referred to as a simple sugar. The monomers are the building blocks of our carbohydrates, and the essential monosaccharides in our body include our hexose sugars that have 6 carbon atoms. So blood sugar, glucose is the perfect example there, fructose and galactose, which are all isomers of one another, right? Because they all have the same molecular formula, but they look different from each other. And then our pentose sugars, which have 5 carbon atoms. So ribose and deoxyribose on the bottom line there are examples of our pentose sugars, which again are isomers of one another. All right, disaccharides. So di means two. So if we take two monosaccharides and we bond them together using dehydration synthesis, we produce a disaccharide. All right, so example of that would be glucose plus fructose would lead to sugar and water. So sucrose is everyday table sugar. Some important disaccharides include sucrose, which I just mentioned, maltose, which is malt sugar, and lactose is what you find in milk. The body breaks these molecules down through hydrolysis in order to digest them. All right, polysaccharides. So poly means many. So if we take a whole bunch of monosaccharides, in fact, we can take up to 1,000 of them or more and bond them all together through dehydration synthesis, we produce a polysaccharide. So here's some important polysaccharides to know. Starch. Starch is what we find in plants. So plant-based foods like potatoes and rice and all of those things you think of when you think of starch. These are things that are relatively easy for us to digest. Glycogen is polymers of glucose in animal tissue. So when you eat the meat of an animal, what you're eating is the muscle of the animal. Glycogen is also found in the liver. Polysaccharide associated with plants. Glycogen is the polysaccharide associated with animals. Cellulose is the component of plant food. It's made of the plant wall. We use it as fibers. It's indigestible, so you and I can't digest this. But what it does is attract water to your large intestine and allows you to eliminate easier. That moves us to lipids. So our next big macromolecule category is lipids. So a lipid is mostly hydrocarbons. So this is mostly carbon and hydrogen. It can also contain oxygen and phosphorus. All lipids are hydrophobic, meaning that they do not like water. You know that you've mixed oil and water or oil and some type of a water-based solution together, and you know that they separate. In water, lipids are not able to form a true solution. They can form an emulsion that I talked about earlier. That's a mixture of solutions that don't permanently mix together. They will settle out. The main types of lipids that we're going to talk about here are triglycerides or neutral fats, phospholipids, and steroids. So triglycerides are the most abundant fat that we find in body tissue. They are composed of three fatty acids. That's where the triglyceride comes from, and a glycerol molecule. So want three tri and glyceride for the glycerol. So you can see what that looks like down at the bottom. You can see what one of those molecules looks like. Their main function is to serve as a major fuel source and energy reserve. So we use fats for fuel and we also store fats so that we have that for energy when we need it and don't have a supply of food readily available. It also assists in the absorption and transport of nonpolar fat-soluble vitamins A, D, E, and K are the four fat-soluble vitamins that we ingest that we have to be able to have fat to move those around and to absorb those. And it also serves to protect and cushion the skeletal system and the internal organs and acts as an insulator to retain body heat. So a little more detail about triglycerides. You have a bigger picture of what they look like over on the right-hand side. So there are two different ways to be a triglyceride. You can be a saturated triglyceride, which means you have saturated fatty acids or no double carbon bonds in the tail of the molecule. So if you look over on the right-hand side, the top molecule, you see the carbons running down the middle. That's the backbone of the molecule. And notice that those are all single bonds. There's just a single straight line in between each one of those. And what that does is allow for these to pack close together so they can just stack on top of each other and that can be an issue. These are straight, rigid chains that pack tightly together, and they are solid or semi-solid at room temperature. So some examples of things that are considered saturated fatty acids include butter and lard. So anything fat-wise that's solid at room temperature, there's a couple of exceptions to that I'll talk about, but butter and lard are the classic examples that we use. Saturated fats are associated with an increased risk in heart disease because those can stack all up and make plaques inside of your arteries. Unsaturated fats have one double carbon bond in the tail. Had a hard time saying that. So if you look at the bottom picture, you see where you have your carbon backbone and then you have that double bond and it creates this bend or kink. And so it's not as as smooth as it was, and they can't stack up the same way in your vessels. So these are all of the things that are liquid at room temperature. So when you go to the grocery store and you're standing there in the where they have all the fats and oils, there's a myriad of things to choose from. And so there's, there's regular vegetable oil and there's olive oil and there's sunflower oil and it goes on and on and on and on. Anything that is liquid at room temperature is considered to be an unsaturated fat. So again, olive oil and omega-3 are examples of this. Unsaturated fats reduce the risk of heart disease. So take a look at the difference between those two molecules. That takes us to phospholipids. So phospholipids are produced by creating a bond between the glycerol component of a lipid and the phosphorus molecule. So we have two fatty acid chains and glycerol attached to a phosphate group. This is a non-polar fatty acid portion of this, and the polar phosphate group create two separate ends of this phospholipid molecules. The head portion of it is hydrophilic. The tail portion, which is the fatty acid, is hydrophobic. And this is really important for cell membranes. In fact, this is what your cell membranes are made of. They're made of all of these phospholipids. So essentially, when we talk about the cell membrane, we think about it like it's some type of an actual structure, and what it really is a ring of fat and oil made of these phospholipid molecules. So down at the bottom, you have a picture, a schematic of what the molecule is composed of. Steroids. The most important molecular contribution to human structure and function is cholesterol, which is considered a steroid. We always think about cholesterol as being a bad thing, but cholesterol actually has a really important function. So it's an important component of bile acids. It's a compound that helps to emulsify our dietary fats. So you know that fat and water don't mix, and mostly what you have in your digestive tract is water. And so when you consume fats, if you don't have something that will allow those two to come together and emulsify, that fat can't be absorbed. And so that is the function of bile. So bile is made by your liver and stored in your gallbladder, and it is an emulsifier. It makes it so that you can absorb fats. They serve as the building blocks, steroids do, of many of our different hormones that we'll be talking about in the second semester. And they also are part of that cell membrane that I was talking about before. And down at the bottom corner, you have a schematic of a cholesterol molecule. That leads us to talking about the next macromolecule, and that's going to be proteins. So proteins are a critical component of all tissues and growth. You are made of protein. So they are organic molecules that are composed of amino acids that are linked by peptide bonds. All a peptide bond is a covalent bond specific to a protein. So it's the same thing that we've been talking about all along. They are built by dehydration synthesis. They are broken down through hydrolysis. So same theme that we've been going on this whole time. Proteins are going to serve a wide variety of functions. They can be structural, they can be support, they can be enzymes, they can be hormones, they can be used for contraction, they can be used for protection. So proteins do a lot of different things in the body. Proteins are polymers, so a whole bunch of amino acids that are all linked up together to make what we call a protein. So more than 50 amino acids linked together is the definition of a protein. So when we look at the amino acids themselves, it is a molecule that's composed of an amino group and a carboxyl group that are covalently bonded together, and they have a variable side chain. So the side chain is the only difference between each of the different amino acids. So there's 20 different amino acids that we look at. They all contribute to the thousands of different things that happen in the human body, but they all look alike. So let's take a look at that picture. So over on the left-hand side, you see the amino group, and then on the right-hand side, you see the carboxyl group. And in the very middle, you see the central carbon that they're all bonded to, right? And then that box that has an R in it, that's the side chain. So again, all of the molecules that make amino acids, they look like this. This is what every amino acid looks like. That little box that's R, that's the parts that's variable. So you can have a lot of different options for what that part is going to look like. Okay, so here is a chart that shows you all of those different amino acids. By no means do you have to memorize this structure or anything like this. I just want you to get the idea that what's in the blue box is that R or side chain or variable portion of an amino acid. So here are all of them on here, the structures of each of them, and you notice what's the same is not in the blue box. So that's the same for every single one of those amino acids, but each one of those amino acids has a side chain, and the side chain is what's different. So again, proteins are formed by dehydration synthesis. They're broken by hydrolysis. In dehydration synthesis, as you remember, a water molecule is removed from the two amino acids. The carboxyl group of one amino acid is going to bind to the amine group of the second amino acid, and that covalent bond that's going to be formed is going to be called a peptide bond. The new amino acids are added to the peptide in the same way. All right, let's talk about the shape of a protein. So the shape is essential to its function, and proteins are not functional until they have a 3D shape that makes them specific. So think about a key and a lock, and how it takes a specific shape of a key to unlock that particular lock. And that is how a protein works. It has to be a specific shape to be able to do its job, so it can bind to its target. It has to have what's called a lock and key. Um, a protein shape is determined by the sequence of amino acids in which it is made of. The sequence or order of the amino acids is called the primary structure of the protein. So we're going to talk about all the different levels, and the first one is primary, and it's just simply the order of the amino acids. The secondary structure, which can take the form of either an alpha helix, which is like a coil, or a pleated sheet, is maintained by hydrogen bonding between the amino acids in different regions of the original peptide strand. So we see their primary region there, our primary structure there, and then we see that we can make some hydrogen bonds in between different amino acids, and when we do that, we form a pleat or a coil. All right, the tertiary structure occurs when we have further bonding and folding from that secondary structure. This tertiary structure is globular in appearance. So when we have our primary structure, which is our order, and then when we have the helix that forms, when that helix forms into a globular structure, a coiled up structure, that's our tertiary structure. Some small proteins are actually functional at this level. And then finally, our quaternary structure. This occurs as a result of interaction between two or more tertiary subunits. So the example that we're looking at here is hemoglobin. This is the protein in the red blood cells that transports oxygen to the body tissues. And so if you take a look at the very last picture in that diagram on your right-hand side, down at the bottom right-hand corner, that's 4 of those globular proteins all bonded together to form that great big molecule. All right. So here's how I think about it. Imagine a string of Mardi Gras beads, and each of the individual Mardi Gras beads is a different color. Each one of those would represent a amino acid. Each bead would represent an amino acid, and that would be your primary structure, the color and the order of those beads. That would be your primary structure. Now I want you to take those beads and I want you just to twist them, and that would be your secondary structure. Now I want you to take that twisted secondary structure and I just want you to drop it into your hand into a big glob, and that would be your tertiary structure. And then I want you to do that in your other hand as well, and I want you to take those two and bond them together, and that would be your quaternary structure. Protein can undergo what's called denaturing. This is a change in the structure of the molecule through physical or chemical means. So things like extreme heat, acid bases, and other substances can cause a protein to denature. And when that happens, it uncoils and loses its original shape. Denatured proteins lose their functional shape and are no longer able to do their job. So some examples of this, we always say, can you unfry an egg? Because an egg is mostly protein. Can you unfry an egg? The answer is no, you can't unfry the egg because once that happens, it changes the shape of the proteins. And so the proteins now aren't able to do what they did before, right? Same thing's true if you curdle milk with acetic lemon juice. When you do that, you can't undo that. So protein denaturing is something we have to be really cognizant of, aware of all of the time because body temperature can affect protein denaturing. So when the body temperature goes too high, it literally causes the functional proteins in the body to stop working because they uncoil or denature. Proteins can also work as enzymes. So as you remember from a previous slide, enzymes are proteins that catalyze or cause a chemical reaction to happen. There is a specific enzyme for each substrate and each chemical reaction. So you have more than 5,000 enzymes that are made by your body to catalyze all of the different reactions that you have, and they're very specific. The substrate must match the 3D shape of the active site. Again, that lock and key idea or a jigsaw puzzle idea. So let's take a look at our picture at the bottom. The green is the enzyme. The substrate is our two items that we're going to start with. And so the enzyme's job is to bond those two together. And so we have substrate 1 and substrate 2, and they are going to fit. Notice that their little parts fit exactly into that enzyme. And when they fit into that enzyme, just like a lock and key, just like a key into a lock, they're going to bond together and form our product, and the product is released. Notice that the enzyme is now empty, and the enzyme can be used again. So enzymes are used over and over and over again until they eventually wear out. Enzymes work by lowering the activation energy that's required for a given chemical reaction to occur. The amount of energy required to get an action started is lowered because of the presence of that enzyme. This increases the speed of the chemical reaction. So taking a look at our graph, we have our two reactants on the far left-hand side. And so we're talking about on the left-hand side, you have what's called the amount of energy. You have to put a certain amount of energy into a reaction to get it to happen. So to get a bonding reaction to happen, we have to put energy in. And so how much energy we have to put in is indicated by the graph there. And then once we've got the energy in, we can create that product through that bonding experience. On the right-hand side, you've got an enzyme that's being used. And notice that we have our two reactants, but notice we don't have to put nearly as much energy in to get the whole thing going. And that's the idea of enzymes. All of the reactions in your body need enzymes to get them going. If they don't have the enzyme, then they can't work. So let me give you the classic example of this, and that's people that are lactose intolerant. They are missing the enzyme lactase. And so when they consume a dairy product that has lactose in it, they don't have the enzymes necessary to get the reaction going. And so they're stuck, right? And so they have this undigestible material in their digestive system. And if you know anyone that's lactose intolerant, or perhaps you are, you know how uncomfortable that really is. That leads us to our very last um, macromolecule or category of organic compounds that we're talking about here, and this is going to be our nucleotides. So a nucleotide is actually composed of three individual subunits, one or more phosphate groups, a pentose sugar, and a nitrogen-containing base, and that could be adenine, cytosine, guanine, thymine, or uracil. Nucleotides are assembled into nucleic acids, which include DNA or RNA or the energy compound ATP, adenosine triphosphate. So over on the right-hand side, they're showing you what this looks like in picture form. So what's in the box are the nitrogen-containing bases. So those are the molecular formulas for those 5 nitrogen-containing bases. And then what they're showing you is how those are all linked together. And so we have a uh, phosphate group. And that's what they're showing you with it's in blue. So your phosphate group. And then you have your pentose sugar, which looks like a pentagon. And then you have your nitrogen containing base. All right. And so those 3 components make up a nucleotide. So nucleic acids are going to differ in their type of pentose sugar. That's how they're different from one another. Deoxyribonucleic acid, or DNA, is a nucleotide that stores genetic information. It has 1 less oxygen, deoxy. That's what that means. And then ribonucleic acid, or RNA, is a ribose-containing nucleotide that helps to manifest the genetic code as a protein. In other words, it carries out the process of assembling that genetic code. When we look at DNA, the 2 strands of DNA coil around each other to form the double helix. DNA is located in the nucleus of eukaryotic cells. It's compartmentalized by the nuclear membrane. There are 4 nitrogenous containing bases that can be found in DNA. They are adenine, guanine, cytosine, or thymine, indicated by a capital letter of the first letter of each of those names. And when we look at how they pair up, we remember that A always pairs with T and C always pairs with G. I'll tell you how I remembered it all those years ago. I remembered it as the 2 pointy letters, A and T are kind of pointy, go together, and the 2 round letters, C and G, go together. So let's take a look at our DNA molecule. Most of you are familiar with what this is all about. The blue ribbon is your sugar phosphate backbone that we saw from the previous slide. The part that we're concerned about is in the very middle, which is where our base pairs are. So a DNA molecule is actually 2 of these strands that are mirror images of one another. So one strand is a sugar phosphate backbone ribbon on one side, and then 1 of those base pairs, and then the other strand is the base pair and another sugar phosphate backbone ribbon. Okay, and they're showing you in the middle, they're color coding the 2 base pairs are what are going to hydrogen bond together, and that's what's going to create that double helix molecule, right? And so they're showing you that adenine and thymine, which are the 2 pointy ones, are red and yellow, and they go together, and guanine and cytosine, which are blue and green, they're going to go together. RNA consists of a single strand of sugar phosphate backbone studded with bases. This is located outside of the nucleus typically. And in this case, there's one important difference is that thymine, which was one of our nitrogenous containing bases, is not used in RNA. Instead, we use uracil. So what is the difference between these two? They give you the characteristics, and then they tell you how are they different in DNA and RNA. So where do we find DNA versus RNA? DNA is in the nucleus, RNA is typically in the cytoplasm. The function of the two, DNA is what holds the information. It is the directory of all of the information, and it directs the process of protein synthesis. RNA is what carries out the actual instructions for the DNA. So your DNA is just like a big instruction manual of all of how to make all of the proteins in your body. And the RNA is going to carry out that function of making those proteins. Where do we find the sugar, or what kind of sugar do we have in DNA? We have a deoxyribose. In RNA, we have a ribose. Our bases, C, G, A, and T, are what we have in DNA, and our nitrogenous containing bases for RNA are the same, except we replace thymine with uracil. And the structural, what does it look like? DNA, of course, is a double-stranded coiled helix, and then RNA is a single strand. Adenosine triphosphate, so ATP, is a energy currency molecule. It is made of a ribose sugar, an adenine base, and 3 phosphate groups. So they show you over on the right-hand side what that molecule looks like. It's classified as a high energy compound because the two covalent bonds that link those three phosphates in that green area, they store a significant amount of potential energy. So here's what happens is we have talked about bonding, and when you make a bond, remember, you store energy. When you break a bond, you release energy. And all this molecule does all day long, every day, is to release energy and store energy, and release energy and store energy, so that the cell has a way of having a constant supply of energy. So energy just can't be freely roaming around. It has to be stored in something, and it's something that it's stored in is a bond. And so essentially what happens is that every time the cell needs energy, it snaps that last phosphate off and liberates that energy. And then the molecule goes about putting that back on and storing the energy in there again so that it's ready for the next use. All right. So the adenine containing RNA nucleotide with two additional phosphate groups is what we really have here.